6.6 mean value theorem. We're going to start with Rolle's theorem. And it says that if f is continuous on a closed interval from a to b and differentiable on the open interval, with the endpoints being equal, of the outputs of the endpoints being equal, there is at least one point C in the open interval where it has a horizontal tangent. So for example, if I have a curve like this, here is A, here is B, and that the outputs of these would be the same, there's one point C that has at least a horizontal tangent. Remember, if we have something that looks like this from A to B, this you cannot take the derivative. It has to be continuous. And then if you have something like this, it is not a closed interval. For this one from A to B, it's not a closed interval, and that cusp is not differentiable either. So these are two situations you have to be careful of. It has to follow these conditions. So let's go ahead and do a couple of examples. If given this function on this closed interval, we want to make sure the endpoints are going to be good for this. So what I did was I took the function and I set each factor to 0 and solved to make sure that they're part of the within the interval, and this one was. So this is good to go. So what I'm going to do is take the derivative and from here I'm going to set it equal to 0. And what I did to find the derivative, I did expand the original function out so that I can get my cubic function and then take the derivative. But then when I set this, when I factor this equation, setting each factor to 0 and solving for x, because I want some point in the middle, and it could be C, but I use the x instead, it cannot be the endpoints. So 1 cannot be included, but at the point here in this interval, I would have a horizontal tangent. So then if I do one more, if I went to take the function and solved it, or set it equal to 0 to solve for x, and I see that this is the only point that I could solve for in here, this one does not apply then. The theorem does not apply. All right, so the best way to start describing the mean value theorem is if you had two police officers that were 13 miles apart and they're on a straight freeway, and a car passes the first officer, and then 10 minutes later it passes the second officer. The second officer pulls the driver over for speeding. Why? Because what we can say is, knowing that it's 13 miles that the two officers were apart, and that the driver went that distance in 10 minutes, which is equal to 1.3 miles per minute, and if we can convert it to miles per hour, it's 78 miles per hour. So at some point, that car had to be going at least 78 miles per hour in order to be able to pass the second police officer in 10 minutes. So the police officer knows for sure that at some point, this driver was going past the speed limit. So if we want to go ahead and do that concept, we're going to use this formula that we see here The slope of 2 points, or the endpoints, has to be equal to the derivative of some point in the middle. So the slopes are the same. Remember, this is slopes of endpoints, and this is the slope of the tangent line within the interval. Okay? So a picture of that would be, even now on this one, if I pick this for my A and this for my B, there's a slope between the 2 points. That's the first half of this equation. But by the mean value theorem, there's got to be some point C that has to have the same slope. These are going to be parallel. So that the same slopes of this derivative, in this case we'll call it C, they have to be equal. So let's do a couple of quick little examples. So number 15 in the textbook says we want to talk about lapse rates in the atmosphere. Concurrent measurements indicate that an elevation of 6.1 kilometers, the temperature is negative 10.3 degrees Celsius, and an elevation of 3.2 kilometers, the temperature is 8.0 degrees Celsius. Based on the mean value theorem, can you conclude that the lapse rate exceeds the threshold value of 7 degrees Celsius per kilometer at some intermediate elevation? So at some elevation in between the two, do we exceed that 7 degrees Celsius per kilometer? So we started with this, with a temperature of negative 10.3 degrees Celsius. And then I had 3.2 kilometers where the temp was 8.0 degrees Celsius. So all I'm going to do is set up this as 2 points. And remember, in this case, I'm going to go ahead and use my Celsius degrees first. Or I'm sorry, my kilometers. So I should have the point 6.1, negative 10.3 degrees. And I have the point 3.2 and 8.0 degrees. And I'm going to set it up as slope. And I see it should be this, which is equal to 6.3 degrees per kilometer, Celsius per kilometer, and it does not exceed 7 degrees Celsius, so this does not apply. This does not exceed what we were asking for, and we proved it by just taking that slope. Let's do another example, 17. F of x is equal to 7 minus x squared, and we want to use this in the interval of negative 1 to 2. I'm going to go ahead and use the mean value theorem and to see at what point inside the interval would have a tangent line with the same slope. So I'm going to go ahead and use 2 points using negative 1, and I should get the point negative 1, 6, and the end point 2. Plugging into my equation, I get the point 2, 3. So I'm going to go ahead and set this up saying that I have the points, and I'm going to use slope formula. And then we want to see if there's some point inside that would have the derivative equal to the same slope. So remember, this is the slope of the endpoints. And remember now also, we're going to look for this. So the derivative of my function, and I'll be plugging in C. I'm going to solve for some C. And then we want to say the original theorem said these were equal, so this had to be equal to -1. So then I solve for C, and I see that it's at 1/2. So that does apply to this situation. All right, one more example. Or actually, we're going to move on. So I'm going to do the zero derivative implies constant function. So all it's saying here is that f is a constant function on this derivative. Remember, if I'm given on a graph a horizontal line, we already know that its slope is 0. And then it would just be a constant function. That is the graph of a constant function. So zero derivative implies a constant function, which leads me to the next theorem. Functions with equal derivatives differ by a constant. So we're implying that the derivative of f of x is equal to the derivative of g of x. So if I wanted to get them both on the same side, if I move the g of x over, this has to be equal to 0. And so from there, if I originally took my just regular functions and had it equal to some constant, and then I went to take the derivative of both sides, and remember, it's just a subtraction of two different functions, and you take the derivative individually, you do get, and the derivative of any constant is 0. So in this sense, this would help improving why the functions differ only by a constant. So let's go ahead and try an example. I'm given the function g of x equals 2x to the 10th. H of x is equal to x to the 10th plus 2. And p of x is equal to x to the 10th minus ln of 2. And the question is, which two of these functions have the same derivative without taking the derivative of every function? But remember, it has to be only differing by a constant. This 2 in front does not appear in the other two functions. So all I'm looking at then in h and p is if there's only constants. That's a constant. And this says minus 2, ln of 2, which happens to be a constant. It's just a number. So these two are the ones that have the same derivative. Number 33, mean value and the police. A state patrol officer saw a car start from a rest stop at a highway on-ramp. She radioed ahead to a patrol officer 30 miles along the highway. When the car reached the location of the second officer 28 minutes later, it was clocked going 60 miles an hour. The driver of the car was given a ticket for exceeding the 60 miles per hour speed limit. Why can the officer conclude that the driver exceeded the limit? So we're going to apply the mean value theorem. So I'm going to go ahead and set up my points as time and distance. So I'm going to start with where the first police officer saw the car. That's the initial starting time and place. And then my other point would be 28 minutes later, and the police officer was 30 miles away. But remember, we're talking about miles per hour, so I'm going to have to convert my minutes into hours, so I'm going to divide by 60. So I'm going to go ahead and set this formula up in slope with slope. I have 30 minus 0, and I have 28 over 60 minus 0. And then when I multiply through and everything, I get 64.3 miles per hour. So the car was going over the speed limit at some point within that 30 miles. The last thing that I'm going to talk about but not have an example of is intervals of increasing and decrease. So suppose a function is continuous on an interval, all points are differentiable, and the derivative is positive at all interior points. Then we say it's increasing on that interval. If the derivative is a negative value, we say all interior points are decreasing on that interval. So that's the end of this section.